Hello, and welcome to Section 2.7, Derivatives and Rates of Change. You need to remember Section 2.1 as we talk about this section. We're going to be revisiting that concept of the slope of a secant approaching the slope of the tangent to a point when you move another point closer and closer to the point you're interested in. So this section is kind of putting everything together that we discussed up till now. You remember how talking about this point approaching P was the concept of a limit, but the slope of the secant is approaching the slope of the tangent. Then we later went on to talk about actual limits of functions where an x value is approaching some other value. What is the y value of the function doing when that happens? So that's where we discovered limit notation. And so remember that what's happening when we're talking about slopes of secants approaching slopes of tangents is the slope function is the change in y over change in x, right? So f of x minus f of a, whatever the x happens to be, that's my q, and over x minus a, the change in x. So this, we should be familiar with that limit notation. So this is just telling us that instead of plugging in, so many different values for q, I'm letting q be represented by x, f of x, and those values of x are getting closer and closer to the value of a I'm interested in. In this case, a is 1 when you're looking at this graph. So let's look at an example of how to use this. So I have the function f of x equals x cubed, and I want to find the equation of the tangent line at the point 1, 1. So using limit notation, I know that I can find the slope of the tangent by taking the limit of the slope of the secants as they approach this point 1, 1. So generalizing that slope formula with the limit, f of x in this case is x cubed. F of a in this case is 1, so f of a is 1 cubed over x minus 1. And then now we know how to evaluate this limit now that we've been through sections 2.2 and 2.3. So this limit is 3. So the slope of the tangent at this point for the function f of x equals x cubed is 3. So now if we want to get the equation of the tangent line, we know that the slope is 3, the point 1, 1 is on the line, so we just use the old slope point form of a line, and that's our equation. Here's another example, but this time with the function f of x equals 4x minus 3x squared at another point. So I do the same thing. My a is 2, so there's my function, right? My a is 2, and f of x is 4x minus 3x squared, and that evaluates to minus 8. And again, my equation of the line, there's my slope of minus 8, there's my y value, and my x value of my point 2 minus 4. Another thing we re-examined in this section that we touched on in section 2.1 is straight line motion. So we have a position function which is given by f of t, and the position function is giving us the position of an object from the origin at some time t. So this is used a lot because position per unit time is velocity. It's a rate. What's the change in position per unit time? So you'll see graphs like this. It's a straight line graph. So time is not graphed here. So this is just showing the position of an object at a time relative, so it's showing the position, the displacement from the origin. So for example, this blue point is the point when the object was 5 meters from the origin, and that occurred at time t equals a. The object has moved 14 meters from the origin now, and that has occurred in h seconds from that time t equals a. That's why it's f of a plus h. So we're looking at relative changes in position and the rate at which that occurs over some time interval h. So remember, the average velocity is the change in the position divided by the time interval. And we know that we can take the limit as h approaches 0. That means that that time interval is getting smaller and smaller, and our velocities are approaching the instantaneous velocity when h is 0. And it's the same type of concept as letting q approach p on a graph. Same concept. But instead of intervals on the x-axis shrinking, units of time here are shrinking. H. So if we take this straight line graph and we turn it on its side, so here's where the position of the object was, and now we graph it versus time. This is a normal XY graph now that we're kind of used to, and this is the graph of that position function. So this shows it starting at the origin. It's going away from the origin. It's reached whatever this distance is from the origin. It must have turned around and traveled back to the origin, and then turned around again and is traveling away from the origin. So notice that even when we graph it like this, at time A, as we let another point approach time A and let those intervals get smaller and smaller, we have that same formula, f of a plus h minus f of a over h. We just have that slope formula. So all this is kind of a recap from section 2.1, but now we're using limit notation and we're not estimating limits numerically or graphically. We can now find the limits algebraically like we learned in sections 2, 3, and on. So we looked at this function before. This is a function that describes an object in free fall after t seconds. And before we estimated it numerically, and we guessed that at 4 seconds the velocity was going to be 39.2 meters per second. And now we can verify that with this limit definition of instantaneous velocity. So our function's 4.9 t squared, and our a value that we're interested in is 4 seconds. So here's f of a plus h minus f of a over h. And when we simplify, we get 39.2 meters per second like we guessed at before from section 2.1. So notice that we can generalize this formula. 39.2, notice that that is 4.9 times 4. And if you look at the algebra done when you simplify for the limit definition, you see why. That 9.8 th that you get from expanding this term, the h gets factored out so that you can cancel it with the denominator, and you're left with 9.8 t plus 4.9 h, but then when you take the limit as h goes to 0, this term goes away and you're left simply with 9.8t. So we can find a general formula for the instantaneous rate of change for this function and plug in any value of t. So we can plug in t equals 1, t equals 2. We can see the velocity at different points in time using this simple formula. Okay, so where are we? We've revisited section 2.1. We've seen that we can estimate the instantaneous rate of change by taking limiting values of the average rate of change. We see that we can estimate slopes of tangent lines with limiting values of slopes of secants. We've seen how to find limits of functions, right, and what that means graphically and numerically. And so now all this comes to the derivative. The derivative, really what we've been looking at in the last few slides here, is the derivative. But the derivative is the concept of estimating instantaneous change with limits on many functions, not just a position function or not just from the graph of a function and talking about secants and tangents. It has much, much, much broader scope. So here's the official definition of the derivative. This notation is read f prime of a, and it's the limit as h approaches 0 of this difference quotient, which we've seen again and again. And if the limit exists, we say the derivative exists. It's differentiable there is the terminology. Alternatively, we can use this other difference quotient. This is kind of more like the average rate of change formula. So we can use both of those formats. So let's go back to slide 10 for a sec. This says find the formula for the instantaneous velocity. So instead of saying that, we could have just said find the derivative of the function s of t. Same thing. So the derivative is also the same thing as the slope of the tangent line. So if you recall, the slope of the tangent line was just, let's go find it somewhere. The limit as x approaches a of f of x minus f of a over x minus a. Well, that looks familiar, doesn't it? That's the derivative. So before, when we were looking at slopes of secants earlier in this lecture, we used this format of the derivative. So when you find the equation of a tangent line, you just find it as you normally would with the slope point form, and that m is just the derivative of the function at the point A. So from our earlier example, we could have just used f prime of 2 or f prime of a instead of using the symbol m for slope. So like I said before, a derivative has much broader uses and applications than just instantaneous velocity and equations of tangent lines. If you have one quantity that's changing relative to another quantity, you can find the instantaneous rate of change in that one quantity with respect to the other, no matter if you have enough data, if you have a function, if it makes sense. So the point is it has applications in many, many, many fields. So what is the derivative telling us about functions? It's telling us we don't need to look at tangent lines anymore. We can simply look at the graph to get an idea of the derivative and vice versa. So since the derivative is the slope of the tangent line, let's look at what's happening with this graph as we move the tangent lines. So So my tangent line obviously has a positive slope. My derivative is going to be positive. As I move the point of tangency, the slope is decreasing. The derivative is decreasing. As I reach a turning point, notice what's happening. My tangent line has a horizontal slope. Has a slope of 0 because it's horizontal, and my derivative is 0. If I can get it right. I probably can't get it right there, but I'm sure you believe me. Now the slope of my line is negative, my derivative is negative. So the value of the derivative is the slope of the tangent line at that point. So I can see what the function's doing anywhere if I know the derivative, and I can plug in a value. So, for instance, I can quickly say that the derivative is positive where the function's increasing, because the function's increasing means its tangent line has a positive slope. And I can quickly say on what intervals is the function decreasing if I know where the derivative is less than 0, because that means the slopes of the tangent lines are negative, which means that the slopes are going down, which means that the function is decreasing. So here's an example from a homework problem. So sketch the graph of a function that's continuous on the domain minus 5, 5, and where you have these conditions. So you have g of 0 is 1. That's giving you that the point 0, 1 is on the graph. G prime of 0 is 1. So this is telling you that at 0, the slope of the graph is 1 in some interval around 0. G prime of negative 2 is 0, is telling you the slope of the graph, or the slope of the tangent line to the graph at x equals minus 2 is 0. So that's telling us that the tangent line's horizontal. So we have a local maximum or minimum or turning point at x equals minus 2. The limit as x approaches negative 5 from the right is infinity. Tells us that at the left end point of the domain, you have a vertical asymptote going up from the right side of the asymptote. And this is telling us that on the right side of the domain, as x is approaching 5, the function has a horizontal asymptote at 3, y equals 3. So there are a lot of different possible graphs, but remember this would be something where you would need to actually draw the graph, not just choose a multiple choice graph from WebAssign in a test situation. So let's start off here. So 1, the slope of the graph at 1 is we're given as 1, right? G prime of 0 equals 1. So the slope of the graph at 0 is 1. So the first thing I would do is draw just a little line segment at the point 0, 1 that has a slope of 1. G prime of 0 equals 1 means the function has a slope of 1 when x is 0. And saying g of 0 is 1 tells me that 0, 1 is the point on the graph. The second thing we took from this, the slope of the graph is 0 at x equals minus 2. So it's a turning point there. So you can draw a little curve at x equals minus 2. Draw local max or min. I drew a local min in this case. The third bit of information, so that it has a vertical asymptote at x equals minus 5, which is on the left side of the domain. So draw an asymptote and draw it going up to positive infinity there. And then the last bit of information, this limit, told us that it's approaching 3 as you're approaching the right side of the domain. So you can draw a function, a curve that's approaching 3. So what we took away from all this today is that the derivative is the same thing as the instantaneous rate of change of a function to a function a. And we can use the derivative with a lot of different applications and function types. So we'll be talking about the derivative again in the next section, but that will be on the next test.